Welcome to CANSSI's Distinguished Visitor Program. My name is John Brown. I'm the Deputy Director at CANSSI and a professor at the Okanagan campus of UBC, located in beautiful Kelowna, British Columbia. CANSSI, in partnership with the Okanagan campus of UBC, is honored to be the host of this inaugural event, and it is with great pleasure that we welcome Peter Guttorp. Peter Guttorp is a statistician who specializes in spatial statistics. Among other things, he is known for making substantial improvements to the accuracy of geostatistical models. Peter is a professor emeritus with the University of Washington and has close ties to scientists across British Columbia and Canada. His work on the environment, climate modeling, and atmospheric modeling relates to UBC's priority area of environment and sustainability. Peter has been recognized within Canada and internationally for his contribution to the study of climate change, for which he was a member of the panel awarded a Nobel Peace Prize in 2007.
What I'm going to talk about today has to do with climate and climate change. And to do that, I'm assuming not everybody knows everything about climate. And I'm also assuming that not everybody knows everything about statistics. If you get bored, there will be a picture soon. I can promise that. So let's start talking about the greenhouse effect. The greenhouse effect is well, heat comes in from the sun. And that's shortwave radiation. And that warms up the Earth. Some of the heat gets reflected by ice and snow. A lot of that heat gets absorbed in water and land. So the Earth gets warmed, and then the Earth radiates heat back. That heat is long-wave radiation. Why does that matter? Well, it matters because short-wave radiation can pass through the atmosphere very easily. Long-wave radiation can't. There are some gases that absorb these long waves, and so they absorb the energy. You have a molecule absorbing energy, it starts moving, and you get heat. The main greenhouse gases are, the biggest one by far is water vapor. Then there's carbon dioxide, which you all hear about as the greenhouse gas. Well, it's not at all the biggest greenhouse gas, that's water vapor. And then methane, which is one of the more powerful greenhouse gases in the sense that it creates a lot of heat when it gets hit by radiation. So the greenhouse effect is something we've known about since the early 1800s. Carbon dioxide regulates how much water vapor there is in the atmosphere. When you heat the atmosphere, it can hold more water, and so you get more of another greenhouse gas. Next thing we need to talk about before we can start talking about anything else is what is climate. Those of you who are not statisticians, this might not make any sense, but for a statistician, climate is the distribution of weather. Here's a not uncommon statement. Climate is what you expect, weather is what you get. Climate is the distribution of weather, weather is a realization of that distribution. So from a statistician point of view, it's something we know a lot about. I'm going to start by talking about measurements. And we're going to talk about how you determine things like global mean temperature. Then I'm going to talk about climate models and how you can use them and how you can compare them to data. Toward I'm going to talk about projections, and then I'm going to talk about local impact. We start with measurements. Measuring global surface temperature. Here's a data sheet. That's one of the things you use. This is from 1761 in Stockholm. Stockholm has one of the longest series of uninterrupted temperature measurements. And I've done some work on that series. We'll see more about it later. So this is for January in 1761. And there are things like it was cloudy, then it rained, then it was cloudy, then it rained between 12 and 8 at night. And then between 8 and 12, it was cloudy, then it rained, then it was cloudy. Here's the Stockholm series, starting at around 1760 and going, I think I plotted it here until about 2005. there's a reason to expect that the minima are going to increase faster than the maxima. And the maxima in Stockholm don't increase that much. So what I showed there was the series as it was recorded. And what I have on the bottom is the difference between that and the adjusted series. So you have a series of measurements, and you know that there's sometimes something wrong. So for example, they found that the thermometer was miscalibrated at one point, and here you can actually see that. They need another correction for urbanization. This observatory was built outside of town, in the middle of nowhere, in the mid-1700s. And by late 1800s, Stockholm had grown and enveloped the observatory. My point is that each of the temperature series has these kinds of problems. And this is one of the really good ones. So let's look at where we have global temperature measurements. Here are the current location of the 3,739 floats last week. And so that gives us some idea of the temperature structure of the ocean. We also collect data from the ocean using ships. So every ship has a log, and once or twice a day they take surface temperature measurement and air temperature measurement. It's usually given in squares. So let's go look at the square right about here, for example. There are 17,000 observations starting in February of 1748. You know, it's very unequally spaced in time, very unequally spaced in space, because ships don't go everywhere. There's some places that have virtually no measurements at all. That's how you measure it. Now you have a lot of measurements, and you're going to combine it somehow. And there are lots of different ways that people combine it. Is there a trend? So here's one way of using a trend. Oh, here's a straight line fit going from 1970 and forward. Here's what you can do. If you don't like that, you can just take subsets. But you have to put them all together in order to see that it's actually warming. So here's the global temperature in 5-year intervals. And you see that Earth is not uniform in temperature, not too surprising. And sometimes it's cold everywhere, sometimes it's warm everywhere. But look at what starts happening now. Getting in early 80s, it's starting to get all yellow. It's all red and all yellow. So that's a climate model. It's usually 500,000 to 1 million lines of codes, usually written in Fortran. Do these models work at all? To figure that out, we have to compare them to data. Global models are very coarse, and therefore you try to do something else. You try to do regional models. You want to know what's going on where you are, and so you try to do a finer resolution model by just looking at the smaller region, so say Europe, North America, whatever, and run the model with boundary conditions to the differential equations given by the global model lines. I'm going to look at projections. Projections is what people in climate science do when they want to talk about the future. Is instead of doing predictions, you set up a scenario. You say, okay, let's put down a reasonable string of land use, greenhouse gas emissions, etc., and use that as our input to the model. What I'm going to talk about now is, and this will be the last piece of this, projecting sea level rise. Now, the thing I really want to emphasize here is that I will be showing you the uncertainty in those projections. And that's the conditional uncertainty given the scenarios. I'm assuming the scenarios are what's going to happen. And I only look at the highest scenario. And here's what happened under scenario 8.5. the highest scenario that it's usually called the business as usual scenario. Here are the observations so far. And here's each red line is one climate model output of temperature. And for this scenario, there are 33 projections. The uncertainty comes from the models, give different answers. The regression of model on temperature on global sea level is uncertain, and the regression on global sea level, local sea level is uncertain. If I want to know when do we hit 20 centimeters, or mean sea level rise, and that appears to be somewhere between now and 2019. That's the level of uncertainty that we have. If we look at the components of uncertainty in 2050, we can say what many agencies do is they output one number. This one number would be some kind of average of all the model projections. And in fact, this is what the Norwegian authorities want planners to use. They want them to say, well, let's take the highest scenario, 8.5, and let's look at the range of the climate models and use that to figure out the 90% interval. But that's not all the uncertainty. There's also uncertainty in our relation between temperature and global sea level. And there's also uncertainty in the relation between local and global. And so we're saying, instead of saying that it's 19 centimeters, or between 11 and 26, we would rather say that it's somewhere between 0 and 40, with reasonably high probability. If we're now going to use that in decision making, how do we do that? There's one approach. It is a fact that Bergen authorities are thinking about sea level rise and want to address it. And they've thought of various kinds of adaptation. So there's an outer barrier that would cost about 30 billion Norwegian crowns to build. It's about 5 billion Canadian dollars. They could bring some inner barriers inside the harbor that would be cheaper, 1.1 billion Norwegian crowns. So what we need to compute is cumulative storm surge damage costs. And then we can see if we can just afford not to do anything. So what are storm surge damage costs? Well, we can get that from Norwegian authorities. They've done that over several years. This is a very long tail distribution. Most of the time it's down here, but occasionally it can be quite big. Then when sea level changes, we don't really know what to do because we don't have estimates for that. So we're going to simulate damages by drawing random annual costs from that very long tail distribution. Sometimes we'll get very large values. A lot of the time we'll get not very large values for each year, independently from year to year. Then we're going to draw random increase factor paths. So how much does it go up with a given sea level? And we're going to draw a random sea level path. And then we look at the upper 95th percentile of the cumulative cost. Goes up. This is on a log scale. 30 billion Norwegian crowns was the outer barrier cost. Well, if we wait till 2038, we risk having had that much cost. We put in the 30 billion before that, we will be doing better. So this is how much will it cost if we just keep waiting. If we just do the inner barriers, we need to do that in 2019, or we risk having things much worse. So this is current work that we're trying to do to illustrate that even with substantial uncertainty, you can get some ideas of how to do a conservative decision. And then the other thing we're going to do with this, we're going to see, well, how long does each of these take to build? How long can we wait before we start building them? So there are lots of stuff that we haven't done yet. But this is results that came out this morning. Uncertainty is your friend. Uncertainty is something that constitutes knowledge, and you can use it to make informed decisions in very uncertain situations. There are some references for this if you're interested. Only my own. But that's what I had easy time. Thanks.